All right, guys, we finally made it. Just a couple days left. Week 9, the last section of Algebra 1. 6.07, correlation and causation. Um, so here in this problem, or in this module, we're going to be looking to see how two variables affect one another. So for example, this first scenario here presents somebody playing video games, and his mother's saying his video games affect his grades. So they want to run a test, basically. Todd here is going to see if video games do indeed affect his homework grade or his grade in class. So he goes, the experiment that they're going to do is Todd's going to take 1 week without playing any video games and see how he does in his classes. Then the next week, he's going to play his video games like normal and again see how he does in his classes. And then they're going to compare the results to see if he performed better or worse, or if there wasn't any kind of change at all. But this is what correlation is. Correlation is finding out whether two variables, like the amount of time playing video games and the grade you have in class, to see if they're connected, to see if they link with each other. Causation is very difficult to prove. We can usually assume that there is a causation, but causation is difficult to prove. Is there a cause and effect relationship happening? Can we say that for sure that what we change about one thing causes a change in another? So correlation is a measure or degree in which relation between two sets of data. So correlation is just saying that two variables have a connection to each other. Like, for example, maybe the time you play video games and the amount of schoolwork you get done. But causation is saying that one thing can be caused to affect another thing. So one variable has a direct impact on the result of another variable. So that's just a quick definition, a quick rundown on causation versus correlation. So what we're going to look at are equations, tables, and graphs, because you can illustrate, you can sort of collect your data and you can analyze it through either making an equation or making a table or making graphs. So there are kind of pros and cons to each, right? And this is kind of a list. So if you have an equation, don't look at this equation for any particular reason. If you're wondering why is it 2x plus 1, it's just a random equation, so don't worry about that. It's just the equation in general. The strengths of it is it's easy to find the exact values because you can just plug in numbers to the equation and get values out. It's easy to update if the equation needs to be changed, and it's easy to make a table of values. But the cons to it is it's hard to visually see. We can't just graph an equation in our head and know what that equation is going to look like on a graph. So it's hard to visualize what an equation would be, what it would look like. Then the second thing, table of values. Now, table of values makes it quick and easy to find exact values like 1 and 3, 2 and 5. Like we know, we can see the points very clearly, and it's easy to calculate the slopes and stuff with that. But what's difficult about it is if you have to update it, it can be tricky if there are certain changes that need to be made. And of course, graph. The benefit to a graph is you can visually see what's going on. It's very easy to read it, to see a trend to it, to see a pattern. But the difficult thing is it's hard to find exact values because you kind of sometimes, unless you have a really good, clear graph, it's hard to really see specific points on the graph. So another thing that we want to see if there's a correlation between is maybe junk food and obesity with teens, right? So you can use your statistical process to kind of see if junk food causes obesity or not, right? See if there's a correlation between there and if there's a causation between them. So 3 years ago, Carolyn's school had a modest obesity rate of 10%. So 10% of the students were obese. She discovered the number of students who are obese increased by 11% each year over a 3-year period. So she's noticing an increase. And she's also looking at her school's junk food, right? She also says that at her high school, She discovered that the school began to sell chips, candy, and soda 3 years ago. So 3 years ago, the school starts selling chips, candy, soda, all this fatty food, and she's noticing that over the past 3 years, the obesity rate in her school has gone up. So she's wondering if the fact that the school has, added these to the vending machines, she's wondering, is that part of the reason that the kids are more obese? So although you can maybe find a relationship there, you might say that there's a correlation. So you got the table of the values, 10%, 21%, 32%, 43% of the students obese over those certain years. You have the equation that you can make from that using the slope formula, y minus y over x minus x, getting the m value and then plugging that in. And you can make a graph of that as well, right? So all this shows, hey, there's a positive correlation. But the problem is, can we really say for sure that even though there is a strong positive correlation between these variables, can we say for certain that it's because the school sells this food that the students are more obese? And that's hard to say because there's so many other factors. What if, what if you guys had quarantine and no one was allowed to go outside and exercise? That would be a reason why people are getting obese. So, there's other variables at play that could be affecting this. So it's hard to really say if it's the school's fault, So this is like lawyer 101 here, That's what lawyers would argue pretty much the whole time. All right, but going back to Todd's and his mom's experiment with the video games. So they recorded their data now, right? So the first week, we got no video games, and we recorded the GPA for Todd. The second week, he played with video games, and you can see the recorded GPA for Todd. Okay. So first off, independent, dependent variables. Independent is the x variable, which is the days here. Day 1, day 2, day 3. Those are the independent variables. Dependent variables is going to be the GPA. How does the GPA affect change over the course of days with or without the video games? So here's a graph of it, right? So we've graphed the data points. So the red graph is the week without the video games, and the blue graph is the week with the video games. Now, just based on looking at that, there really doesn't seem too much of a difference. You might say that he did a little bit better without the video games overall, but ultimately his grades weren't that bad, even with playing video games. So there might be a correlation between video games playing and Todd's GPA or Todd's performance in class, but you can't really say for certain that there's a strong correlation or a causation there. You can't say for sure that because Todd plays a lot of video games, that's going to cause his grade to go down. So there are some questions to be had about that information. But it does say here that he did slightly better without video games, but there really isn't a significant change. We haven't really done a lot of math yet. We've just sort of talked about definitions and kind of things that you need to know, information you need to know. We're going to do that even more here. I'm not going to do any math yet. We're just going to keep talking about stuff. So correlation and lines of best fit. We talked about lines of best fit in the last video. Hopefully you guys did your project okay with that. The correlation coefficient. So correlation coefficient is a value. We call it the R value. Right here, right? R. So we say like R equals or something, right? The correlation coefficient is basically a number that measures how strong a correlation between two things are. Let me go to this real quick, and I'll make kind of a picture for you to help you understand. So let me draw a graph. Let me do this black. Okay, so I'm going to draw 5 graphs for you. All right, so the graph on the left is going to have a strong negative correlation. So a strong correlation meaning that the points are pretty much in a perfectly straight line, and it's negative because the points are going in a downward trend. So this right here is strong negative correlation. The next one I'm going to show you is another negative correlation, but a slightly weaker one. So you can see all data points. They still trend in a downward pattern, but they're not as tightly compacted in a line. It's not a perfect line. So this is a more weak or moderate negative correlation. So weak or moderate negative correlation. The little graph in the middle, I'm going to have no correlation. So it's going to be just a random bunch of points, no pattern to it at all. So no correlation. The fourth graph I'm going to do is it's going to be a positive correlation, but it's going to be kind of weak. It's not going to be a perfect straight line. So this will be a weak or moderate positive correlation. And then the last one, I'm going to make a perfect positive correlation. So a perfect straight line up, right? So this is a strong positive correlation. And so now you would use a number called the correlation coefficient to measure how strong this correlation correlation is on these. So that R value ranges from -1 up to +1. So this is our R value. So R value can only ever be between -1 and +1. It's never going to be, it's always going to be within that range. So the R value can never equal 2 or -2 or anything like that. It's only going to be some decimal between -1 and 1. And in the middle, of course, is 0. Now, I've lined up the graph that I made here perfectly with my correlation coefficient. If your correlation coefficient, if R is equal to -1, you're going to see a graph like this. It's a perfect negative correlation. So -1 has a strong correlation, but it's negative, meaning it trends downwards. Whereas +1, R equals a +1, is another strong correlation, but it's positive, meaning it's going obviously the upward direction. Now, the closer you get to 0 in either direction, the less correlation there is. So 0 is actually, exactly no correlation. So if your R value, if R equals 0, that means you have absolutely no correlation. Now, you might have a moderate or weak positive correlation at maybe if the R value is equal to 0.5. That's when you would see something like this. It's definitely positive because the R value is a positive number, but it's not 1 and it's not 0, right? Somewhere in the middle. So it would be something similar to this graph. Same thing on the negative side. If it's a negative 0.5, it's a weak but moderate negative correlation. So that's kind of how the scale works. So if I gave you a graph that looked like this, I would say, based on those data points, it's not perfect, but it's definitely a positive correlation, and the data points are pretty close together. So I wouldn't say that it's R equals 1 because R equals 1 would be, a perfect straight line, but you can see the data points are not that far spread out. So I'd maybe say R is equal to 0.8, something close to 1 because of how close the points are. Now, if I say the points are more spread out, so if I make the points more spread out, then that number is going to drop. My positive correlation, it's still going upwards, but you see how spread out my data points are? So maybe that's 0.4 or maybe 0.3. Now, if I make all the data points completely random, and there really isn't a line anymore in the middle, it's just a bunch of random points, then it drops all the way down to 0, 0.0 or just 0, right? It's not even positive anymore, it's just no correlation. Right, now, if I start making a negative trend, you can see that here these data points are going kind of in a negative direction, but they're very spread out. That might be a negative 0.4. But the straighter your line gets, the higher that value goes. So if the data points are very slightly spread out, but not very spread out, then that value is going to go up. So R in this case would be like R equals negative 0.7 maybe. But a negative, remember, to indicate that it's negative correlation, a positive would indicate the same thing, but the upward direction. So that's correlation coefficient kind of in a nutshell. It's basically a scale from -1 to +1 that kind of measures how tightly your data points are, packed together they are. The more spread out they are, the weaker they are, the more in a line or in a row they are, then the stronger it is. And the correlation coefficient is just a number to measure that. So if I asked real quick, if I said, hey, graph, make a sketch, sketch a graph of a correlation coefficient that was like negative 0.3, then I would expect you to make a graph that had a negative trend, But being a negative 0.3, being a small number like that, I would expect that negative trend to be very spread out. So something like that, right? If I said make a graph where the R value was 0.9, right? I would notice, hey, it's positive, so my graph should have a positive trend, should be going upwards. 0.9 is very close to 1, so I would think that my line, its data points would not be very spread out. It'd be very much in a almost like a perfect line, but not quite a perfect line. So that's how the correlation coefficient works. That's pretty much what all of this stuff here says. So when you look at this data value, Donald calculated the correlation coefficient of R, which normally you wouldn't do this by hand. If you want to get the actual R value, you would use a graphing calculator to do that. So obviously we're not going to try to make it ourselves. We're just going to know what it means. So his correlation coefficient was 0.0764. Now 0.07 is very, very small. It's very close to 0, right? It's not 0.7, it's 0.07. Which is extremely small, which means it's very close to 0, which probably tells me that there isn't a very strong correlation. That's probably almost 0, right? It's almost no correlation at all. And that's what that answer down there said. So correlation again versus causation. So, it's well known that smoking can cause cancer, right? But there's no definitive proof because we can't just go out and make an experiment where we say, hey, here's a bunch of people. We want you guys to smoke a lot, and then we'll see how many of you guys get cancer. That's not really ethical, right? That's illegal. So you can't really conduct an experiment. But what you can do is just take real world data and analyze it. So we notice out in the world that out of the people who do smoke cigarettes, we notice that those people tend to get cancer more often than people who do not smoke cigarettes. So without doing any kind of experiment, we just look at the data in the real world and we say, hey, maybe there is a causation there. Maybe smoking does cause cancer. Now, we can't prove it, so to speak, but we can kind of tell simply because the people who are smoking are getting cancer and the people who are not smoking are not getting cancer. But like I said, you can't really, it's hard to prove it because you can't really do a controlled experiment on it. Same thing with eating breakfast and success in school. So they always tell you as a kid, eat a good breakfast so that you're, ready for school and your brain's functioning. But can you really prove that? Can you really prove that eating a good breakfast will make you perform better in school? Not really. There are other variables at stake here. Like, for example, if people who don't eat breakfast are more likely to be absent or tardy, so of course their grades are going to be bad. It's not because they're choosing to be bad or maybe because they're just not up for it, but maybe there are other things going on in their lives which are causing their grades to be bad other than just not eating a breakfast. But yes, you can say that you've seen people out there who do eat a good breakfast before school, and a lot of times those people do perform better. But again, you can't really prove it because there's a lot of other things that we don't know that could be kind of affecting the results there. Again, we talked about correlation. We talked about the values being between -1 and +1, positive or negative. And causation. Like I said, causation is difficult to prove, but we can kind of infer it a lot of times. Again, not a lot of math here. But we'll see if we can do any kind of math. So for a charity fundraiser, a tennis pro is trying to hit tennis balls as hard as he can to see how far they will travel. Here are the results. So the speed was 30 kilometers an hour, 32 kilometers an hour, 29 kilometers an hour, and 36 kilometers an hour. And then he's got his distance. So at 30 kilometers an hour, he hit it 60 meters, 32 kilometers an hour, he hit it 61 meters. And you can see the results as well. Right, so we would make a scatter plot, which is to graph all of this. So if you make a graph over it, here that graph would be. You guys know how to do that. You've got the speeds down here at the bottom, and then you've got the distance over here on the left-hand side, and you just plot your points. And you can see that it goes upwards, meaning that we can see that there's a positive correlation. Obviously, the information we could take out of this is that the faster he hits the ball, the further the distance it will go. Because if he hits it 29 kilometers an hour, it only went 58 meters. But when he hit it 36 kilometers an hour, it went almost 70 meters. So the faster he hits it, the further it goes. So that's what a scatter plot can do for us. We can plot these points on a scatter plot, and we can see that it trends upwards, and we can know there's a positive correlation there. Of course, we calculated the line of best fit the last video round. So this is not a perfect line of best fit. Yours could be very similar, but slightly different from this. But how you would calculate it is you would, draw a line of best fit on here, and then try to use 2 points that you can find the slope of and make an equation of. So again, we talked about all that in the last video. If you still have questions about that, just let me know in the discussions tab. I'll be happy to try and answer them or make another video showing you to do that step. Hopefully you remember how to do that. But they've made up their own equation. Again, if you were to make up your own, it might be slightly different than this, but it should be pretty similar. So they have an R value of 0.98. Now, 0.98 is very close to 1, which tells me that this would be a very strong correlation and very positive correlation as well. It's a positive number, and it's very close to 1. We talked about that scale before. 0.98, R equals 0.98 is obviously very close to R equals 1, so it would be a very strong, very positive correlation. And that's what that says there. And then lastly, so a twin brother and sister are measured yearly. Their heights during the first 5 years are shown here. So brother, 1 year, 24 inches. His sister was 25 inches, or sorry, 26 inches in 1 year. After 2 years, the brother was 31, sister was 30. 3 years, 34, 32, right? You guys can see the data there. Which of the following statements is true about the data? The brother and sister have strong positive correlation in height, but it is not 100%, therefore the R value is not 1. Or the brother and sister have a strong correlation in height, but we cannot tell if it is either positive or negative. Increasing age causes height increases in both boys and girls. We can say this because the correlation coefficient is almost exactly 1. This is really tricky. I'm not even sure what I would answer here. We definitely can tell that their heights are going up. If you're comparing their heights over time, the brother's height goes up over time. The sister's height goes up over time. Obviously, they're not going to get any shorter. I definitely know it's not going to be the second one, because we definitely know that there's a correlation, and it would be positive because as the years go up, the heights go up. So the fact that we don't know, it's saying we can't tell if it's either positive or negative is wrong, because we know for sure it's positive, so it can't be that one. This one says they have a strong positive correlation in height, which makes sense, but it's not 100%. Therefore, R value is not 1. I mean, I agree with that. It's not going to be perfect, but, the increasing age causes height increases in both age and both boys and girls. We can say this because the correlation coefficient is almost exactly 1. It's really hard to say. I'd probably go with this last option, but I'm wrong, as you can see. This is the correct answer. Why did it say that last one was wrong? Just out of curiosity. The correlation coefficient tells the strength of correlation and is positive or negative. It does not imply causation. So this is assuming that there's a causation there, whereas this one was not. So that's, I guess, why I mixed them up. But no big deal. And is that it? That's it. That's the last thing. So good luck. Everything now it's just a quiz for you guys. So good luck on it. Again, if you have questions, let us know. Remember, you got 3 attempts, make them count. Make sure you like your grade, because this is your 4th quarter grade. So if you have any other quizzes that you can go back and fix because you have extra attempts on, please go attempt those other quizzes to try and get a higher score. Remember, the highest one is kept. So even if you perform worse on it your second time around, the original high score will still count. So don't be afraid to take it more than once, because the highest score out of your 3 attempts is the one that will be graded. So good luck. And again, let us know if you have questions in the discussion tab. See you guys next year. Have a good summer. Bye-bye.